Hey everybody in Calc BC, welcome to lesson 7.6, Geometric Power Series. As with this whole unit, we're going to be in the second half of College Board's Unit 10. Today we're talking a little bit more about Taylor series, power series, etc. So I've honed in on lesson 15 here, representing functions as power series. We're going to be looking specifically at geometric series today. And how a geometric series, which is one of the very first series that we learned about back in our Unit 6, how can that be transferred to a power series when we have x involved, right? So yeah, so let's just kind of see how that works. Let's switch over to the notes. All right, here we go, geometric power series. So today we will learn to find a power series for a rational function by recognizing the function as the sum of a geometric power series. Remember, a rational function means a fraction with a polynomial in the numerator and in the denominator. We're going to use a geometric power series to represent that function. Before we start, let's do a quick review of geometric series. Geometric series are formed by multiplying by a common ratio r. Geometric series is in the form the summation from n equals 0 to infinity of a times r to the n. We often saw that with n starting at 1 going to infinity and then displaying each term as a times r to the n minus 1. I want you to think about how this form and this form of a geometric series really mean the same thing, right? Let's say that we're starting with n equals 0, then the first exponent is a 0. If we're starting with n equals 1, 1 minus 1 means that the first exponent is still a 0. So these series are just different ways of writing the exact same thing. So it doesn't matter if you think about it like this or like this, like we're used to. It's the same idea. So suppose I told you to start with a equals 2 and to let r equals 3. What geometric series would you write? This is all review so far, but we could write this as the series from 0 to infinity of 2 times 3 to the n, right? Or if you wanted to start with n equals 1, it would be 2 times 3 to the n minus 1. And that means we're going to have 2 plus 2 times 3 plus 2 times 3 squared plus 2 times 3 cubed, etc. That's what that means. So what if a was 2 and r was negative 3? Well, we could do the same thing. It'd be 2 plus 2 times negative 3 plus 2 times negative 3 squared plus 2 times negative 3 cubed, etc. That's going to become an alternating series, right? Because every other term is going to be negative. But what if we went a little bit further and stretched this idea? What if r was x? Could we write out this series? And the answer is yes. It's going to follow the same exact pattern. We just have an x instead of a 3 or negative 3. So this time it's going to be 1 times x to the n. So we're going to end up with 1 plus 1 times x plus 1 times x squared plus 1 times x cubed, etc. And that is just a fancy way of saying that you can have an x in a geometric series and the pattern is still the same. We can use our knowledge of geometric series to help us write a power series for the function if the function can be written in the form a over 1 minus r. We know that a over 1 minus r is the sum of a geometric series. So we can say that a over 1 minus r equals all of these things added together, right? So if a geometric series in the form that we're familiar with, a times r to the n, converges to the sum a over 1 minus r, where a is the first term in the series and r is the common ratio, it converges and that's the sum. So what we can do is we can start with the sum and end with the series. That's kind of what we're going for here. So let's take a look at this example. Find a power series for f of x equals 1 over 1 minus x squared centered at x equals 0. Give the first 4 non-zero terms and the general term. So if you take a look at this fraction, we know the sum of a geometric series has to be a over 1 minus r. So in this fraction, we're carrying about that number, and it's a really good sign that this number is already 1, so we don't have to worry about that. So our a is 1, and our r is x squared. So we want to give the first four non-zero terms and the general term of the series version of this of f of x. So we have 1 over 1 minus x squared, and that really equals, let's see, what is it? Let's follow the pattern from above. So we have the first term is just 1. The second term will be 1 times x squared to the first. Then we would have 1 times x squared to the second. And how many are we doing? 4 non-zero terms. So we have 1, 2, 3. We need one more. 1 times x squared to the third. And then we need to know what the general term is. Let's just kind of figure out what the pattern is first. So we have 1 plus x squared plus x to the fourth plus x to the sixth. So I think it's pretty clear the pattern is that we are adding 2 to the exponent every time or doubling whatever n is. So it would be 2 times 1, 2 times 2, 2 times 3. So we could say it's x to the 2n. So that is our first 4 non-zero terms in our general term of our power series. Then the question says, for what values of x does the series converge to f of x? And to figure out when a geometric series converges, it's when the absolute value of r is less than 1. That's when we converge. I'll write that out. Converges when the absolute value of r is less than 1. So let's apply that in this context. RR is x squared, RR. Our r is x squared, so we can plug in x squared for r. And that has to be less than 1. So if the absolute value of something is less than 1, it means that the actual value of the thing without the absolute value bars has to be sandwiched between -1 and 1. And if we think about what values of x are going to make that work, it could be anything, again, between -1 and 1, right? X has to be between -1 and 1 to get an answer that's x squared that's between -1 and 1. So that is our values of x when our series converges. Okay, so there you go. I don't know why I keep changing the way I write a 1. I wrote it, with the extra lines here and not over here, but whatever. Let's finish this up. So let's say that we were going to graph our functions here. So we're going to graph 1 over 1 minus x squared, our actual function, our rational function, if you will. And then the first 5 terms of our series, or the infinite series, is exactly equal to the function. The first 5 terms will be an approximation. And so I'm going to graph both of those and then think about what happens. So I already graphed these on Desmos, so we could take a look. So I'm going to pause this real quick and switch over to Desmos. All right, so here I have graphed y equals 1 over 1 minus x squared. That is the function that our series is approximating or equivalent to when we have infinite terms. But we are only graphing the first 5 terms here. So if I turn this second plot on, you'll see that the green curve is an approximation of the red curve only for this top portion. And that is between -1 and 1, which is what we found when we figured out when our series converged, right? So think about that. Let me switch back over to the notes so we can examine the algebra again. Okay, so you can see we found that our series converged between -1 and 1, and that's exactly when this actually works on the graph. So it's only for the middle portion between those 2 vertical asymptotes. So what did we notice? Our power series only models or approximates the function 1 over 1 minus x squared when -1 is less than x is less than 1. Right? That's what we found. Okay? So that's what it means when we say find when this series converges. It's when does it actually exist? When does it actually model the original function? So it's only between -1 and 1 in this question. All right, we got a couple more questions to do on the back. So let's flip on over. Find a power series for 12 over 4 plus x centered at x equals 0. Find the first 4 non-zero terms and the general term. So what we need to do is force this fraction to look like the sum a over 1 minus r. That 1 is non-negotiable. This is a 4, not a 1. So we got to do something to figure out how we're going to make that into a 1. We have options. In this question, what I'm going to guide us to do is to just think about multiplying the top and the bottom of this fraction by 1/4. And what we end up with is 3 over 1 plus 1/4 x. And that's not bad. That's closer, right? A is allowed to be any number, so 3 is fine. The only problem now is that we have a plus instead of a minus. So I'm going to rethink this as 3 over 1 minus -1/4 x. And that's because we have to get into this form, a over 1 minus r. So now that we have something over 1 minus something, we can say that a is 3 and r is -1/4 x. We got to be able to do that. So that's what we wanted there. And if we think about if we are centered at x equals 0, we are. We'll prove that once we actually show the series. But wherever we're centered, remember, it would be x minus c. We would have minus something, and that would show up in our r, but we'll get to that. So let's write this as a series. So 12 over 4 plus x, our original rational function, is now going to be thought of as a geometric series with this first term 3, and we're multiplying by the common ratio of -1/4 x for each term. So the second term is going to be 3 times -1/4 x. The third term is going to be 3 times -1/4 x squared. We need the first 4 non-zero terms, so we're going to need one more term. And the general term, okay, well, let's just stick with what we know, which is that we have 3 times -1/4 x to the n as our general term. No need to get any more in depth than that. I don't want to have to, cube 1/4, figure that out. Question didn't tell us to, so we're just going to stop right there. That is good enough. We found our series. And now you can see that in each parenthesis, we don't have minus or plus anything. So we are centered at x equals 0, so that's good. And what else? We need to know what values of x make our series converge to f of x. So we're going to take our r, and our absolute value of r must be less than 1, we know. So I'm going to stick positive 1/4 x between -1 and 1. And if I multiply by 4 on all 3 sides of this inequality, we'll get -4 is less than x is less than 4. So that's where we converge. That's the domain of this power series, and that's where it equals 12 over 4 plus x. Okay? All right, let's try one more. Find a power series for f of x equals 5 over 4 minus x centered at x equals 3. Give the first 4 non-zero terms and the general term. So if we start with 5 over 4 minus x, and we want to think about how do we get this to be a over 1 minus r, so something over 1 minus something, but also centered at x equals 3. If we're centered at x equals 3, the way that we're going to want to do that is in these parentheses for each one of these terms, just like any sort of Taylor series, we want to have an x minus 3 because we want x minus c to show up in there. So what I'm going to write over here is we want to force r to be x minus 3. so that we can be centered at x equals 3. So is there any way that we can get x minus 3 to be in this spot? So let's think about that. It would be great if this could be x minus 3 subtracted from something, hopefully a 1. Because if we can get that, then we'll be in tip-top shape. We'll be in good shape because then we'll be centered at x equals 3. So what's going to happen right now, if I distribute this negative, we're going to have negative x, which is part of our original denominator, and negative times a negative 3 is going to be plus 3. So isn't it true that if I have 1 plus 3, I'm going to get 4? Well, yeah, it is. So we just did a little bit of manipulation, and lucky for us, this fraction was set up for success for us. We were able to turn the x into x minus 3, and the 4 magically became a 1 because once I distribute this negative and combine like terms, I'm going to end up with the original denominator. Sometimes it's a little bit more work, but you basically want to force the second term, the r, to be what we need it to be so that we're centered in the right spot, and then we could multiply by something like we did up in the first question. If the first term still wasn't a 1, we'd have to, for example, multiply by 1/4. And this question just magically worked. So on top, we got a 5, and on the bottom, we have 1 minus the quantity x minus 3. So in this question now, we have an a of 5 and an r of x minus 3. So that's what we needed. So we're trying to do the first 4 non-zero terms and the general term. So we could say that 5 over 4 minus x could be represented as 5 plus 5 times x minus 3 plus 5 times x minus 3 squared plus 5 times x minus 3 cubed. There's the first 4 non-zero terms. I'm not going to be distributing. I'm not going to be foiling. We're just going to leave it like this. It's nice and tidy and neat and organized, and that's what we like. And the general term is going to be 5 times x minus 3 to the n. So that's part of our answer. Then we want the general term. No, sorry, we did the general term. That's what this is. Then we want to know what values of x make our series converge to f of x. So just like before, we're going to take the absolute value of r and make sure that that's less than 1. So we're going to plop that between -1 and +1. And if I add 3 to all 3 sides of this inequality, we're going to get 2 is less than x is less than 4. And indeed, if you think about that, we have to be centered at 3. You can tell that 3 is halfway between 2 and 4. So our domain here, or the values that make our series converge, are centered around 3. So that's what we wanted. So we found it. Okay, there we go. Very nice. That's the last question. So hopefully that made sense. Let me know if you have any questions, and have a great day.